we continue on with our discussion of derivatives, and here we want to talk about electric circuit elements. And so the problem we're given talks about QT denotes the electrical charge in coulombs of an element of an electrical circuit at time t in seconds. V of t is the voltage in volts across the element at time t, and we're given equations for each one of those. And then it wants I of t to denote the current in amps through the element of time, and P of t to denote the power in watts consumed at that time. And it wants us to give expressions for each one of those. And what is the maximum power consumed by the element? So we have to know a little bit about circuits to start off with. So here's the functions that it gave us. It talks about Q, which is our charge in coulombs, V is our voltage in volts, I is our current in amperes, and P is our power measured in watts. And each of these being a function of time, that it changes over time. One of the first things we need to know about it is about current. And so the thing we know about I, which is current, is it is the rate of change of charge. So we think about this with an electrical circuit. We have some sort of charge, which is some amount of electrons flowing, that's changing over time. That's how we get our current. To think of that in terms of derivatives, then we can say that I of t is the derivative of q with respect to time. And if we think about that in terms of units, again, we've used this notation in the past when we've done previous things, but just a reminder, this means has units of, well, Q is in coulombs, so our change in Q over our change in time, which has seconds, and a coulomb per second is an amp. So that's one way we can make sure these things work out. So we know that our current is going to be the derivative of whatever our charge function is. The other one we need to deal with is helping figure out how we're going to use voltage to determine power. Well, one of the definitions for voltage is the electric potential of a charge to do work. So it can also be defined as the amount of work per amount of charge. Or again, in derivative terms, it's the derivative of work with respect to charge. And if we think of it in terms of units, work is going to have units of joules, Q is going to have units of coulombs, and so it actually turns out a joule per coulomb is the same as a volt. Not a common definition that you'll see, but one that's going to be very useful to us. For power, what we find is power, as we're a little bit more familiar with, is the rate of work per time. So the amount of work we do divided by the amount of time it takes is an indication of power. So it is the derivative of work with respect to time. So again, if we think of that in terms of units, it's going to have units of joules per second. And a joule per second is a watt, which we would certainly find that one on any conversion sheet. So that still leaves the question of how we're going to determine power from the information that we have here. Well, one of the things we can do is by using what is called the chain rule. We can break this apart and know that if we're trying to get work with respect to time, we can take the derivative of work with respect to charge times the derivative of charge with respect to time. And if we multiply those two things together, just like you hoped it would be, you would see that the dq's cancel out. We get watts and dt, and that works. And this is called the chain rule, which tells us that we can split that if we multiply, we can multiply functions together with respect to derivatives and work those out. So how does that help us? Well, as we said above, if we look at this equation, that's P. The dW with respect to dQ, that was voltage, which we know. And the dQ with respect to T, that is I, which we know. So you may have also commonly seen that power is voltage times current. So that's an equation that would come up really early in electronics. So now we can use those to actually solve our question.